Morning, guys. So yesterday we introduced the chemical technique of a titration. That technique here is very commonly used to find the concentration of an unknown. We saw how we did that was we actually ran it through a chemical reaction. Our unknown in our example was an unknown concentration HCl. It could be really concentrated, like really high molarity, or it could be really, really dilute. How we actually figured out how much HCl there was we actually reacted it with controlled amounts of NaOH. Basically, I drop in the NaOH here slow enough. I want to make sure that I hit the equivalence point that I just added in the last drop of hydroxide to exactly match up how much acid particles there were, making sure that you don't have any limiting excess kind of issues there. That way, we've counted the HCl. I knew how much initial volume the HCl was in, and I just simply do a moles divided by liter, and that gives you your unknown concentration. If the HCl here happened to be really, really concentrated, it would take a ton of volume of NaOH before that equivalence point was reached. If it was very dilute here, it would just take less volume. Based on how much volume, it just ends up as a stoichiometry problem. What I want to demonstrate for you in this lesson here, this is actually a virtual lab, so it actually provides us a virtual environment. I'm going to actually demonstrate for you a titration in action here. This lab setup here, I don't know if you can read it here, it's written up into two parts. Part one of the experiment here, we have two unknown solutions. One of them is an unknown HCl, the other is an unknown NaOH solution. Now they do help us out a little bit here. They say, well, the HCl here is tested to be about 0.1, the NaOH here is about 1 molar. That doesn't sort of defeat the purpose of titration though. Titration's here, if I do it now, I can standardize the NaOH, I can get more significant figures. So I might know the ballpark is about 1, I want to know to more significant digits, well, what is it actually? What I'm going to do here is in part one of the experiment, we're going to start off with what's called a primary standard. Our primary standard in this case here is going to be KHP. It is an acidic standard here. If you remember, a primary standard is a solid and it is a very, very pure compound. So that if I scoop out a certain mass of the solid, let's say it's 1 gram again, for that 1 gram, because it's so pure, because it doesn't absorb water or react with other things in the atmosphere, when I weigh out 1 gram, I'm really confident that the 1 gram is exactly this chemical. If I then dissolve it into a liquid, I know that concentration very, very well. So first thing I'm going to do is I'm going to demonstrate for you the proper technique in making a solution. Once we know that concentration really well, we're going to use that solution as an acidic standard. I'm going to use it to standardize the NaOH. I'm going to use it to find the NaOH concentration. Once I know the NaOH, it becomes a standard solution. I can use that as now a base standard, and I can use that to standardize HCl. We'll do that in part 2. So without further ado here, we're just going to switch over to our virtual lab bench. Just like in a regular lab bench here, we can pull out a whole host of different glassware. We can do beakers of many sizes, Erlenmeyers, pipettes, barrettes, and whatnot. I can pull out some tools as well, Bunsen burners, weighing boat, scale. Where I can find my solutions is on this left-hand sidebar here. So again, I'm going to just try to separate this for you here. We're doing part 1. If I want to pull out solution, I can either double click the chemical or I can just drag it and drop it into my purple lab bench here. So I'm just going to grab the KHP. You notice it's animated as a solid. This is a primary standard. Part 1 is going to take this acidic standard, run a chemical reaction between these two to standardize the NaOH to get more precision on this NaOH solution. Once I have that, I can then use that to standardize my HCl solution. We notice the concentration that they've given us here is widely different. I'll also demonstrate for you the proper technique in doing a dilution as well. So without further ado here, let's just make our first acidic standard first. Again, for a titration, you have to know one of the concentrations so that you can use it to find the other unknown. So what I'm going to do here is I'm going to pull out my scale so I can weigh out how much of a chemical I need to dissolve it in. I'll show you the calculation of how I get this number here. I need a vessel to actually dissolve it in. Beakers are really good for dissolving because they actually have a very, very wide mouth. You can just take your stirring stick here. When you add water to it here, it's really easy to do. So I'm going to take my KHP here. I'm going to drag it over the beaker. On the bottom here is this transfer bar, and you probably won't be able to see that here. I've calculated what I want to do here is I want to make my acidic standard here roughly close to the concentration of my NaOH. Because if these concentrations that I make are not close at all, either I'm going to run through a lot of one chemical or the other chemical is going to change color within a drop. So I do want them to be fairly close here. They already told me it's approximately 1. I'm going to figure out how much mass until it can be approximately 1. You'll notice here that the scale is already measuring the mass of the beaker. What you can do here is you can actually tear the scale, basically reset this 0, and basically you can just weigh out the mass that we want here. In this case here, I want 18.38 grams. So I'm just going to go down to the transfer bar window here and I'll type in here 18.38. Again, I'll show you the math of how I calculated that number later on. You can either press enter or press the pour button over here, and there we go, it's animated. Okay, we scooped in that there. This balance here is actually really, really precise. Most of our scales are only 1 or 2 decimal places. If you go on to chemistry here, there are what's called analytical balances, and they really do have 4 digits of precision. They're trying to be really, really precise. So I'm going to remove my KHP here. I have my solution. I'm going to dissolve it in water. The standard solution I want to make here, I've calculated for making 100 mils of your standard solution. In this case here, unfortunately, the beaker, although it has markings, is not very precise for volume readings. So what I'm doing here, even though I pre-weighed it in a beaker, eventually I want to make my solution in what's called a volumetric flask. A volumetric flask here is way more precise. Even though the volumetric flask itself, it only has a single marking. This single marking is really, really well calibrated. This is the size 100 ml volumetric flask. So by the time the water is exactly this level, I know pretty much it's exactly 100 milliliters. The only problem with the volumetric flask is because it has such a narrow neck, it's going to be really hard for you to take a stir stick and dissolve the powder inside the volumetric. So I'm going to sort of do best of both worlds. I put it in a beaker. It has a very wide mouth. I'm going to drop in some water. Again, my beaker is just a holding vessel. I don't really need to look at the labels here. I know eventually it needs to be made up to 100 milliliters, but because the beakers are so imprecise, maybe I'll start off just transferring, say, 30 milliliters. Just something less than 100. You can imagine taking a stir stick here, mashing up some of that solid, and then what we can do is we can slowly transfer these rinsings into the volumetric. I'm going to transfer in my 30 mils. You'll notice it even animates for us here. Well, there is a little bit left over, maybe leftover solid that hasn't dissolved, maybe leftover liquid. Because I was way under 100, I'm pretty confident, okay, I can add some more water here. Let's say I add another 40. Let's make it different here. Maybe I'll dissolve the rest of it. That'll rinse down some of the sides. I can transfer it in to my volumetric. My goal here is to just make sure I am under the 100 ml mark. I added in 30 and 40. It looks like in this container here, yep, so there's some imprecision. There's still some extra volume here. Let me just pour in that extra. I don't know how much there is. Let's tell it, pour it 10. No, there's still more there. Pour it 10. What I want to do is I just want to make sure all those rinsings are under the 100. Because once I'm in the volumetric flask, I can slowly add water to this one here. I don't want to overshoot this line here, because if I get it too high, then again, I don't know the concentration really, really well. So far I've added in roughly about 80 or 90 milliliters. Usually you can take a graduated cylinder here. So I'm going to pull out a graduated cylinder. I'm going to pull out a 25 ml grad cylinder. I'm going to sort of pre-fill it here. Let's pre-fill it with 25, sure. Okay. And I'm going to slowly take my graduated cylinder and I'm going to add it to my volumetric flask. Because the graduated cylinder here is a lot more precise than a beaker, I can measure a little bit more fine-tuned increments here. I'm going to transfer in, let's say, 1 milliliter at a time. I can press enter or press pour again. And what I'm looking for here, it'll actually animate if you can see it close enough here. This volume here is steadily climbing. You should see in a second here, this volume here is going to get pretty close to that 100 mark that we're sort of zoomed in at. Even the grad cylinder here is sort of losing its volume. When you get up really close to the top, the best technique here is actually to take one of those eyedropper pipettes, squeeze it in, and you can actually drop it in sort of like a fraction of a mil at a time. So those eyedropper pipettes here, maybe I drop it in 0.5 at a time here. I want to be really, really precise so that, maybe I even want to do 0.1 for the remaining of it here. I want to make sure it hits this mark because this volumetric flask is really well calibrated. Because this is a water-based solution, it forms that meniscus shape here. Remember, we want to read the bottom of the meniscus. And there we go, because we were careful enough here, we've now made a standard solution from our primary standard, which is KHP. We're going to use this as our acidic standard to titrate against the NaOH. So for titration here, the other type of glassware that we need here is a burette. The burettes here, they do come in many shapes and sizes, but in our case here, we have a 50 ml burette. What I'm going to do is I'm going to put the base in the burette. Remember, the 0 mark is at the top, the 50 mils are at the bottom. Usually what I tell people is just fill the burette here something more than half. What I don't want is, I don't want it to be running low on the burette and I haven't still finished the titration. Anytime I need to reload the burette sort of mid-trial, that's going to introduce error. I just want to make sure there's enough volume in the burette so that for one trial that I'm testing, there already is enough base to actually do the titration. So usually I say more than half. So take this Erlenmeyer here. You can use a funnel if you feel safer with it. Again, in total, it would be about 50. Let's transfer in, let's say 40. Again, there's that transfer bar at the bottom here with the 40. I press and enter. It even zooms in for you here. I don't know if you're going to be able to see this here. This is currently between the 11 and 12 mark. They sort of zoomed in for us here. Remember, the numbers are upside down. That's why the 11 mark is up top. always remember to take down the initial volume reading. So just clicking over my burette here. Actually, I might need to drag it over again. For my burette here, the number divisions here give me that 11. I'm just going to jot that down here. So my starting value is 11. These tick marks here is 0.1, 0.2. It looks like the bottom in this case is past 0.2. And I'm going to actually eyeball or estimate one more here, maybe 11.23. That is my initial reading. Be careful, that doesn't mean there's actually 11 mils in the burette. If the 50 mil is down here, we have some 30, 40 mils in there as I had poured it in. But what we're going to do, like we did yesterday, we're going to take a reading now. When the titration is done, I'm going to take another reading. By subtracting those two numbers, it will then give you how much volume you actually dispense. So that's going to be my base solution. I'm going to have my acidic standard here ready. I have 100 mils, so I have more than enough that I need. Usually what we have is just pulling out an Erlenmeyer on the bottom here. I'm just going to pull out a couple of these Erlenmeyers because, again, in the titration here, I want to actually do multiple trials just to make sure it's reproducible. So I'm going to have these three here. What I'm going to do is I'm going to put 3 different samples of my acid into these Erlenmeyer flasks. I'm going to pipette my standard solution here into these 3, and then I'm going to titrate against this NaOH. It's just better chemical technique here if you actually take your volumetric flask here. I know I made the solution 100 milliliters. I'm going to pour that 100 milliliters. You can pour it into a clean beaker here. You might be surprised by the time you pour it in 100, it may not exactly line up with the 100 ml mark on the beaker. That's totally fine because we're actually just using the beaker as a containing vessel, as a holding vessel. What we're going to do now is we're going to pull out our pipette. Burette is the nice long one that I filled the NaOH here for my pipettes. Also comes in different sizes, 10 and 25. The first set of titrations I'm going to do for you is going to be with the 10. So I'm going to just pull out my 10 ml pipette here. A pipette here works like a straw. You can drag the pipette over top. Again, the transfer window at the bottom here, I'm going to type in the 10. This time, instead of just the pour button, releasing solution here, I can actually withdraw. I can suck up solution here. In the past, chemists used to actually pipette by mouth. You can imagine that was a real big safety concern. Nowadays, they just use like a suction bulb here, and they basically create that negative pressure to withdraw a solution. Again, just like your volumetric flask, although it only has one line, the pipette only has one line here. It is really, really well calibrated for. That 10 milliliters here, when I line it up at that 10, I can just drag it over, and I can just dispense that 10 back into my Erlenmeyer. As I'm doing this here, I'm actually getting a few different what are called aliquots. Aliquots are the fancy name for a fraction or a sample, a portion of your stock solution here. So I'm going to pour in 10 into each of these flasks here. I'm just getting ready for 3 titrations. So 10, I'm going to withdraw it. Each of these solution here is referred to as an aliquot. Right. So once you've done that here, I prepared my 3 solutions here. Now I'm pretty much ready for my titration. We saw one last cheat from yesterday here. Unfortunately, the NaOH as well as the HCl, they are both colorless solutions. So although I do need the NaOH here to slowly count how many acid particles there are, I need something to tell me that the reaction is done. I need something to tell me to stop at this point here and then take the volume reading. That thing here was an acid-base indicator. The one that we chose was the phenolphthalein. Phenolphthalein here I mentioned yesterday, it remains colorless when it's in acid. It turns to a pink color when it's in base. You don't need a ton of it, it just needs to be present. So take this phenolphthalein here, it already is in liquid. I'm going to pour in, let's say, 3 drops, about 3 milliliters or so. Pour that in. I'm going to transfer it in. The most common problem with the titration is people forget to add in this indicator, and they're like, oh, how come it's not turning pink? It's probably because there's no indicator there. So just make sure you have indicator in all 3. At this point here, we're ready. So I'll repeat. I have my NaOH here in the burette. I'm going to drag my burette here over top of my first titration. Make sure you take a starting reading. Sometimes people get into the groove and they're like, okay, I'm ready, and they forget this number here. Without that starting number, I can't actually subtract a difference. Usually when you do a first trial here, it's just an approximation because, again, I may not know that this is about 1 molar. In this case here, I actually do. But what I'm going to do is I'm just going to roughly estimate here. I'm going to pour in a couple here. I'm at currently 11 point something. Maybe I'm going to drop in maybe 1 milliliter at a time. There's a little stopcock valve at the bottom of the burette that you can slowly open and close. It's really fine-tuned so that you can drop in little droplets of solution as you need. So what I typed in here is I'm going to transfer in 1 ml at a time. I'm just going to keep pouring it in, and I'm going to keep waiting for the solution to turn pink. I don't want to overdo it. If I overshoot it, there's now an excess, and now I don't have a good count of how much acid there is. So I'm going to start from that 11. I recorded that down. Start transferring in here 1 milliliter at a time here. So I'm just going to pour that in. I don't know if I dragged it on top. There we go. So I just poured in the 1 milliliter. Let's pour it in some more. I'm looking for when that Erlenmeyer flask here actually changes color. I don't really need to keep track of how much volume because I can read later on. Notice here, hey, now the indicator turned to a pink color. That means I've dropped in enough base to kill off all the acid here. Now that the indicator notices that there's excess base, extra base particles, it turns to pink color here. Remember, the first one is just an approximation anyways. In this case here, I look at the V final. The V final here, it says it's also between 21 and 22 because I dropped in 1 mil at a time here. No real surprise, this one here is 21.23. I've dropped in exactly 10 milliliters, all right? Now, it's possible that I may have overshot this one here. I just want to get about what it is. I don't want to wait forever. I don't want to drop in sort of 1 mil at a time, like 0.1 mil at a time until I know roughly I'm close. So now with my first titration, sort of that's a waste. That's going to be my outlier. I'm going to pull my next solution out here. Because I have enough burette volume inside, I don't need to refill yet. I'm going to take my 21.23. I'll do it without error here just so that it's more simple here. I knew the first titration took about 10 milliliters here. What I can do here is I can open the burette here. I can very safely toss in, I don't know, 7 milliliters because I know I have upwards of 10 before the acid runs out. So I'm just going to pour in 7 here. Take down your initial reading, 21.23. I'm going to pour in the 7, so that's going to drop down. And what I'm going to do here is between 7 and 10, I'm going to add it in smaller fractions. Maybe 1 mil at a time was a little bit too intense. I'm going to actually add it in, let's say, in 0.5 mils. So as I added in 0.5 mils here, I would have added, let's say, 7.5, 8 mils, 8.5, 9 mils. Now I know it's pretty close, somewhere between 9 and 10. Maybe I want to drop that down even. Let's go in 0.1 milliliters at a time. So let's go 9.1, 9.2, 9.3, 9.4, 9.5, 9.6, 9.7. I'm looking for the first instance of the pink color. They actually animate this for you really well. This is called your endpoint. This pink color here would be overshot. This one here is the one I'm looking for. This one would have extra base. I wouldn't have exactly a good count of HCl, whereas this one here, the color should stay about 10-15 seconds or so. I'm going to take down this reading here. So I notice that it's actually somewhat less than 10 here. I'm going to go 31.02. I just record this on the side so I can tabulate for you later on. If I just did a subtraction right now and just figured out approximately how much solution is in there, it's only 9.79. So the 10 mil was overshot here. 9.79 sounds better. I want to see if my third trial here is consistent with that here. I technically do have enough volume, so my burette here still has a reading of about 31. If it's only taking about 9 mil, I will only be down to about the 40 mark. I just want to make sure I'm not past the 50 mark, even though the burette here will still have a little bit of volume below the 50. If I sort of pass the markings, I now no longer can read the final volume, and I now have messed up the experiment. So just to reassure me a little bit here, I can actually reload the burette at any time I want. So I'm going to take my anyway solution here. Let's reload it. Let's reload it with another maybe 20 milliliters. Let's just be safe, right? I just want to show you that you can reload if you're not in a titration. All that's going to do here is it's going to change my starting volume. So my starting volume here, again, just coincidentally, it ended up being 11 point something again. This time it's 11 point maybe 02 or so. It's okay to reload in between, but while you're doing a titration, it's you're not allowed to reload or else it's going to introduce error. So now I'm going to drag it over top of my Erlenmeyer here. I know from my second trial it's about 9.79. So this time I'm even confident here. I know the 11 mils mark is here. I'm going to transfer in 8 mils, or you basically open it until it's about 19, because that should be totally safe, right? Both of them didn't change color until it was about 9 mils something. So that's 8 mils in the solution. Let's transfer in 1 mil, right? So that it's 9 mils now. Let's transfer it in, let's say, in 0.1 intervals here. So 9.1, 9.2, 9.3, 9.4, 9.5. Now the other one started changing color somewhat close to this. So maybe I'm going to do 0.05. So 9.55, 9.65, 9.65, 9.70, 9.75. Oh, it's looking like a little bit pink here. Let me see if 9.75, 9.76 maybe. So let's pour it in. And just doing smaller fractions, 9.76, 9.77, 9.78, 9.79. And you're looking for the faintest possible pink color here. If you put it up against a white background here, it should show. In this case here, it's a pink color. So there we go. We have our solution here. This one, it's between the 20 and the 21. So I'm going to say it's 20.8. 20.8, and it's going to be 80. We can always read our burette readings to 2 decimal places. If I just did a quick subtraction there, I can show you roughly what volume that is, 9.78. All right, so that's part one of the experiment here. In doing those titrations and counting how much acid there is, I'll switch over later on to show you the calculation for concentration. While I have the virtual simulation on here, I'm going to now take this NaOH solution that I have. I've now standardized it. I now know the molarity really, really well. I'm going to use this molarity, the 1 molar-ish that I know, and I'm actually going to calculate and standardize another unknown HCl. So this is going to be part 2 of your experiment. Remember when I mentioned here, it's good to have the concentrations here roughly the same. If I really took this concentration here, it's about 1 molar. It's going to take very little drops to titrate something that's only 0.1 molar. Remember, the goal is keep the concentrations here similar so that you're having to dispense in quite a lot of volume here. I don't want the color change to happen too quickly or too slowly. I don't want to waste a lot of solution. 1 molar and 0.1 is just way too big a difference. So what I would do here is I would probably want to do a dilution of some sort. Maybe dilute this one down by a factor of 10 or so, make this one about 0.1. When they're comparable, then that will give you a little bit more fine-tuning, a little bit more detail for when that color change happens. So there's my NaOH solution here. I don't want to use it as is. I'm going to actually do this dilution. So what I can do here, again, the most accurate piece of glassware here is a volumetric flask to do the dilution in. I'm going to dilute it into a 100 ml volumetric flask. It could be the rinsed out one from before, or just take a brand new one here. Again, unfortunately, the volumetric only has the single mark for 100. I can't pour in, let's say, 8 mils, 10 mils, or whatever. I wouldn't know how to measure that. You have two choices at this point here. You can use a burette, because a burette here is so fine-tuned. You can use this and dispense exactly the volume that you want. Say I want to dilute 8 milliliters or 9 milliliters. I can get it from here. That's going to be somewhat more precise. The other way you can do it here, maybe a little bit easier, is using a grad cylinder. I'm just going to pull out another grad cylinder here. Again, what I could do here, if I can dilute it by a factor of 10, just to show you, because I have the advantage of a grad cylinder here, I don't necessarily need to max out the 10. Let's take the stock solution. Let's pour in, let's say, 8 milliliters. So I just dragged it over. In the transfer bar here, I'm going to press 8 mils, press in the pour. Now it's lined up for the 8. Notice the graduated cylinder also has more markings there. I have my 8 mils. I'm going to dilute it into my volumetric flask, pour all 8 mils inside. I'm just going to type in a bigger number than 8 just to make sure it all goes in. So there is my concentration. The concentration is intensive. So imagine this was orange juice here. If you pour it a little bit into a cup, the taste of the orange juice in the cup is going to be the same as the pitcher. So concentration is intensive. It stays the same. And what we're going to do here, probably not using the entire water jug, but maybe putting in a beaker of some sort. But basically, I'm going to add it up to the mark. Because the mark here is going to be at 100, I have about 8 mils. Let's pour in, let's say, 90 mils, right? So that should be about 98 then. So let's pour that in there, right? And there we go. We're pretty close to the mark. When I get really close to the mark here, again, you'll take a water dropper pipette, and basically you're going to add it in really, really tiny fractions. So I'm about 98 right now in our simulation. Maybe I added in maybe 0.2 at a time here, just little squeezed droplets out of the eyedropper. And basically, I'm looking for the bottom of the meniscus to hit my 100 mils, maybe a little under there, and there we go. Remember, if you accidentally overdo it here, now the concentration is way too dilute. I don't actually, not way too, but it's a little bit too dilute. Because I don't have that marking here, I now don't have the precision I want for a titration. So we're going to take our diluted solution here. You should label all these ones here. Let me just clean up a little bit here. So I have my diluted NaOH here. I'm going to use my diluted NaOH here to titrate against HCl. The things that I can remove here, because it's the magic of a virtual lab, you can just highlight them and just press the delete button, and voila, they're gone. So we have our solutions here. I'm going to pull out my burette. You could totally now put the acid into the burette and whatnot. Eventually, they just have to be added into each other. Because I like seeing the pink color up here, I'm going to still take the NaOH. Sure, it's been diluted here. It's been made up to the mark of 100. Again, I'm going to fill my burette something more than half. The 50 mil is marked down here. Let's pour in, let's say, 35 mils. Right? It could be something totally random. You're just going to need to take down what your initial reading is. In this case here, it's between 16 and 17, so let's go 16.22 is my starting reading. This time, I'm just going to demonstrate for you here. You could also do a titration. So far, we've done a 10 mil pipette. You saw that our titrant volume was somewhat less than 10 here. That actually loses a little bit of precision. One way around that, without having to do really fancy dilutions like I just did there, what you can do is you can pull out another size pipette. I'm actually going to demonstrate some titrations with actually a 25 ml pipette instead. So let's grab a couple of clean Erlenmeyers here. Again, because it's the magic of a virtual lab, you can even Control-C, Control-V, like copy and paste. And there we go. We just grabbed a couple of clean Erlenmeyers. This time I'm going to take my unknown HCl. I know it's about 0.1, but I don't know the precision. I'm going to drag my straw, which is our pipette, over top of the 0.1 mole HCl. Again, I'm going to type in my transfer window here, 25. I'm going to withdraw that up, pull that up as an aliquot, put the 25 in here, dispense that 25 here, do that a couple times so that I can ready the few trials. 25 with the withdrawal, so soak it up like a straw, and then put it back down here, 25, and one last time, 25. At this point here, we're about ready for it, but again, what we don't want to forget here is we need the indicator. We need the thing to show me that it's pink when the reaction is done. So phenolphthalein here, I'm going to drop in, let's say 3 milliliters. I'm going to put in the pour button, so just make sure that gets poured in. The actual amount doesn't matter. You can pour in 5 mils. It just needs to be present. So I just go pour in to each of these solutions. Again, just verifying because phenolphthalein is colorless in acid, that's why these are staying colorless. This time, even though it's unknown concentrated HCl, I'm using a lot more volume to test, which means even if I know the concentrations are going to be roughly similar, they're about 0.1 molar now, I'm going to expect to need about 25 milliliters here. Again, the first trial here is just sort of a little bit of a wash up, just sort of figuring out about what it's going to be. If I was completely, I don't know how well I did that dilution, and I don't know how concentrated this one is, I might just do 1 mil at a time. That is actually a fairly large increment on a Brett reading here. So I took down the initial reading here. Let's just pour it in, and let's just wait till this one here turns pink. So the animate set for you just drop. We're going to look for the first instance of the pink color here. Should be getting pretty close. You're going to find in a real titration, the pink color actually stays for longer and longer as we get closer to the endpoint, because it's getting harder and harder for the acid to actually find base particle. That one I was actually cutting really close here. You'll notice I'm basically at the 50 mil mark. If I go any lower than the 50 mil mark, sure, there's still solution in the Brett here, but I have no other way to measure it. So that actually worked out perfectly here. I'm going to take down what the Brett says. So it's between 49 and 50. I'm going to take down here 49.23, let's say. Let's do a quick subtraction here to figure out about what volume that I just tossed in. So just do that there. It says here 33.01. Why is it so much more than the one from before? Again, first thing is totally different set of solutions, but the biggest reason here is instead of just using a 10 ml pipette and testing 10 mils worth of acid, I actually have 25 mils worth of particles, and I'm counting all the particles in the 25. So it took about 33.01. I definitely don't have enough solution here. What I'm going to do is I'm going to refill my Brett. This time I'm going to be a little bit safer here. Let me fill it up with, let's say 45 milliliters. Let's go pretty right up to the top. You can refill the Brett here anywhere in between. Between trials, no problem, but you can't do it within a trial. So right now here, there's my Brett reading here. I'm going to drag it over my second trial. My second trial, make sure you do your initial reading. In this case here, it's 4.22, let's say. I'm going to do my titration. The other one took about 33.01. I should be pretty safe tossing in just 30. So I'm just going to type in 30. Basically what you would do is you would line up, well, I'm about 4. 30 past 4 would be about a little bit past the 30 mark. You just pour that in there. If I've done that right here, good. So that sort of saves me a little bit of time here. Now I do want to do a little more fine tune. That one I accidentally overshot. Now I want, maybe it's somewhere between 30 and the 31 that I calculated, 33 that I calculated. Let me just drop it in, let's say 1 mil at a time. So just pour it in. So this would now be 31, 32. Now the other one started changing color around here. So let's add it in maybe a little bit slower. 32, let's add it in 0.5. So 32.5. Nope, still no color change, but I know I'm getting really close. Maybe I'm going to add in 0.1 at a time. Again, the whole goal here is to be really, really precise, to look for the first instance of that pink color. So 31.5, 30, just going to keep adding there. Should be getting really close. I'm looking for the faintest pink color. You don't want to accidentally overshoot this one here. And let's see if I do this accurately here. You should be able to see the pink color steadily appear. You can imagine trying to do this kind of really small interval here from the start. That's why we do the first one just sort of approximately what is it going to be, and then this one afterwards. So this one here, nope, doesn't look like it's changing color. I can actually verify, okay, let me make sure that I put phenolphthalein in there, right, just to add a couple, oh, so there you go. So that's just actually, okay, my mistake here. Maybe I forgot to drop in the phenolphthalein. I actually had overshot the endpoint, but I didn't know that, right? So in that case there, whoops, that's an outlier here. Phew, at least I still have one more trial. Maybe I'll just do the last titration for you here. This time I'm just going to verify that I have phenolphthalein. Again, the actual amount doesn't matter. I'm just going to make sure that something is in there that can actually change color so that it can tell me when the endpoint is done. I definitely don't have enough volume in the burette, so again, I'm going to just load up from the burette, just something more than half again. Let's load up another 40 if I have it there. Hoping I have enough, so 21 maybe. So let's see if it's cutting it pretty close here. So 21.22. You see there's all of these sort of problems sort of come along the way here. We have a 25 ml sample here. This one here may actually not be enough, but we'll give it a shot anyways. The other thing you could do is you can say, oh, I actually don't have enough solution. Of course, I can dilute another sample, but the problem is if I dilute the NaOH, even if I use the same recipe, 8 into 100 ml volumetric flask, there's always going to be a little bit of uncertainty here. The concentration here would still be a little bit different. So the best thing we can do at this point here, because I don't necessarily want to remake the solution here, and I'm worried I don't have enough in my burette, maybe what I'm going to do here is I'm going to, instead of testing 25 mils like I did, let's go back to testing 10 mils. So let's just see here. So again, just sort of simulate for you. These are some things you might think about doing. Let's take out a clean 10 ml pipette here, and let's just go back to dispensing 10. So 10, let's withdraw that solution here, suck it up into the pipette, and that way when I just test 10, even though the concentration is going to be still the same, this is not going to use nearly the same amount of volume. So if I'm only testing 10 milliliters, I'd expect there I only need about 10, and in this case here I have about 30 in the burette here, I should be fine. So again, I took my starting reading here, that was the 21.22 or so. This time here, again, I only have one sample left, so I do want to be a little bit more precise if I can. So 21.22, let's add it in 1 mil at a time. So here we go. So pour it in 1, 2, 3, 4, 5, 6, 7, 8. I know it's probably going to be about 10. I made the concentrations here roughly equal. If I don't know that, I'm just sort of guessing and checking anyways. So it's going to be 8 right now here. Let's drop it in. Let's say 0.5. So 8.5, 9, maybe 9.5, still nothing. I should be getting pretty close here. So let's drop it in 0.1. So 9.6, 9.7, 9.8, 9.9, 10, 10.1, 10.2, 10.3. Oh, there we go. That one I'd still say slightly overshot here, but it's a good approximation. I already started dropping it in almost at half drop speed. And basically, I'm just going to take a reading. You didn't need to sort of keep track of am I 10.1, 10.2, whatever. You just wait till the pink color appears, take a final reading on the burette, and basically that's your volume. So in this case here, it's going to be 30.05 maybe. And I'm going to show you that titration. I'm going to make a note to myself. That one there was only for 10 milliliters, and that's why that volume is different from the one from earlier. So let's just switch over to our OneNote, and then I'm going to show you how these calculations work out. Okay, so let's just recap on some of the main numbers that we have seen so far. Remember, this lab here is separated into 2 sections. So we have part 1. Part 1, what we did is we created a KHP solution from our primary standard. We had used KHP to standardize a unknown NaOH, which we were told was about 1 molar. Remember, KHP here was a solid. I had told you, I'm going to dissolve in 18.38 grams here. I just want to show you roughly how I get that number. KHP here, I'm not going to give you the whole formula here, but it does have a molar mass here of 204.22. Remember, what I want is between the burette concentration, the NaOH here, and the KHP, I want it to be fairly close so that I'm not wasting tons and tons of solution. This is way more concentrated. Or if the titrant here, we call this top solution here the titrant, if my top solution is way concentrated as compared to the bottom, basically within a matter of a drop or two, the color would have changed already. So the goal here is to make the solution here roughly similar. What I can do is I can calculate here, what if I wanted a KHP here of about 1 molar? What I did is I made a solution that was a little bit less than 1 molar. I wanted to make a let's say 900 molar solution. So here I can just do some stoichiometry here. How many grams would I need? Remember, what I did is I started off with some powder. We pre-dissolved it in a beaker because the beaker was nice. It has a nice wide mouth. Eventually, what I did is I transferred it into a volumetric flask. That volumetric flask here only has one single mark, but that one here is calibrated for 100. We pre-dissolved it here. I poured it in. I rinsed it a little bit here. I poured that rinsing in. Just make sure it's something less than 100, and then eventually I just made it up to that mark. So eventually this amount of powder here will be in 100 milliliters. That gives me my volume. So I want to make 0.10000 liters of this standard solution. The concentration I want to make here, I want to make it a little bit less just in case it's not quite 1 molar here. 0.900 moles per liter. Right. And then based on the molar mass here, this one here, 204.22 grams for a given mole. I'm going to multiply those through 0.1 times 0.9 times 204.22. This is giving me here 18.38. If you just follow the sig figs from there, you would say, well, I'm limited by the precision of this. But remember, we are actually making the solution. So it's actually depending on the precision of the other numbers. Great, my volumetric flask here had a lot of precision. Our molar mass here has 5 digits here. If my scale actually gives me more precision, my scale actually gives me 4 sig figs, that will actually help me get the concentration here to actually 4 sig figs. So that's actually a good thing here. It's actually giving me 1 extra digit there. We then made the solution here. We pulled out the aliquots here. Our unknown acid here was 10 milliliters. 10 milliliters of our KHP solution. This one here we actually happen to know. It's 0.900 molar. This is a pipette here, so that one actually has 2 decimal places as well. The titrant we used in both experiments here was just NaOH. So far, they just told you it's about 1 molar. I want to know exactly what it is. So what I did is I took down a starting reading. After the reaction turned pink here, I took down a final reading. I'm just going to write these trials down for you. So trial 1, 2, 3. These are the numbers that I jotted down for earlier. This is the NaOH that I added. So if you want to follow on your notebooks here, I added 11.23, 21.23. So that was overshot. It was 10 milliliters. Then I didn't need to reload, so 21.23. I added close to the endpoint here. I was a little bit more careful. So this was only 9.79. And then I was worried I would run out here, so I refilled. You can refill between trials, no problem, but you can't refill during a trial. So when I refilled it here, I just took down a reading. We were back up coincidentally about 11.02. Remember, that doesn't mean we have 11.02 in solution. It just means that's our starting mark. It's always the difference that we're interested in. After the reaction was done, when I was really, really close to the endpoint here, I subtracted off 20.80. All these numbers here should have error, but I just want to demonstrate to you the calculations, 9.78. At this point here, you have to use your judgment. If all 3 numbers here are really wildly different, I would just average all 3. In this case here, because the first one was sort of a wash anyways, it was sort of a, I just want to get about what it is. I don't want to have to add 0.1 mil at a time for 10 milliliters. That would take way too long. So the first one just gives you approximately what it is. I just labeled it as an outlier. What you can do here is you can just take the average between the close trials. So average your close trials. In this case here, if I had the extra decimal place, it would be 9. You just add the 2 divided by 2, 9.785 like that. But again, because we're only limited to these 3 digits here, this would still round back to 9.79. So this says, on average, what volume of titrant did I add in? I needed 9.79 mils of the base to kill off all the acid that's in solution. At this point here, although it was really tedious to actually get to these numbers here, right now here it just ends up as a stoichiometry problem. KHP reacts with NaOH. It actually reacts in a 1-to-1 ratio. We're going to get NaKP, the salt, and then H2O left. Obviously, there's other parts to the chemical as well. Let me just write down the numbers as we know them. The KHP I decided to use was 10 milliliters. That was from the pipette. The concentration I had made was 0.900 molar. Notice I have a lot of precision there. Yes, they had given me the NaOH was about 1, but the whole point of a titration is to find out that in more detail. I can even keep that as a complete unknown here. But from the burette, I actually know that the volume we used was actually 9.79. What we can do here is our stoichiometry problem. I want to calculate the concentration of NaOH. Usually I tell people, you start with the chemical that you know more things. So in this case, I actually know more about the KHP. I'm going to start with this volume. I'm going to convert it right to liters because I know molar is actually hiding moles per liter inside. So I'm going to multiply this by 0.900. Remember, that was from my primary standard. When I dissolve that exact 18.38 grams, I know the concentration really well because it's really, really pure. The mole ratio here would be for every 1 part KHP, there is 1 part NaOH. Again, this right here will feel a little bit weird here. We're used to top unit cancels bottom unit. I actually do want to keep the mole unit on top. All I need is pick up liters on the bottom. You saw us do this yesterday here. If it confuses you, you can just type in this first part. out of there, you would actually know how many moles of NaOH did you actually titrate. This moles here was currently in the burette, and all you would need to do is you would need to divide by a volume. So take whatever number comes out of there. Remember from yesterday what we did is we just did it as a reciprocal. Well, the volume of NaOH that I used was this 9.79. Again, I'm going to convert that into liters. So that way it's moles per liter at the end. Crunch those numbers through. 0.01 times 0.9 divided by 0.007979. And this gives you concentration 0.9193. Unfortunately here, because my titrant volume here, like I mentioned, because this was not quite 10 milliliters, if it was 10 milliliters and above, it would be 4 sig figs. This one here is only a 3 sig fig number. So even though I have a lot of precision here, I lose that 3 precision, 0.919 molar. Now I know my NaOH here is 0.919, which agrees, it's about 1 molar. This is now called a standard solution because I now know the concentration. So known concentration. Then what I wanted to do was I wanted to do part 2. Part 2 then took this NaOH solution and it was trying to take the NaOH as I knew it and is using that to find some unknown HCl. So KHP is no longer in the picture anymore. I'm using something that I know the concentration of. Only problem is right now they were already telling me it was about 1 molar. Right now I know it's exactly 0.919 molar. The HCl, they said it's only give or take about 0.1 molar. Again, the concentrations are too wildly different. If I dropped in such strong base into HCl, within a matter of a drop or two, this one here would have already changed color because it's 9 times more concentrated. So what we did experimentally is we had diluted it. I didn't know exactly the concentration. I think the ratio that I did was 8 milliliters from the Grad Cylinder, and I made it up to the mark. Here's a practice of your dilution formula. I took 8 milliliters in a Grad Cylinder, so lots of markings here. I could read 8 milliliters. The concentration is going to be 0.919 molar. My Grad Cylinder will also typically give me 1 decimal place if not 2. So let's say 8.00. Again, I'm losing some precision there, so that's milliliters. And then what I did is I dumped that into the volumetric flask here. Sure, again, you might need to dump in some rinsings as well. But again, your volumetric, it has a nice narrow neck where if you only have the one mark, that mark there is going to be exactly 100.00. So dump what's in the Grad Cylinder here into this volumetric flask here. And you basically add it up to the mark. You'll notice I'm not actually adding in 100 milliliters. Because there already is about 8 milliliters, if I added 100 on that 8 milliliters, I'd be at something at 108, something like that. What I want is I want to just make up the difference, add up enough water, be really close up to the top here, add it up so that I'm exactly at the 100. Don't overdo it or else I have to redo this dilution. So in this case here, I did a dilution. I have my numbers there. For your dilution, you can think about your stoichiometry. C1V1 equals C2V2. Our starting concentration, I had standardized it as 0.919. The starting volume is going to be 8 milliliters. What's the new concentration? I know it's diluted by a factor of about 10, but I want to know exactly what it is. The volumetric, again, has 2 decimal places of precision. I divide these numbers through. 0.919 times 8 divided by 100, and that gives me another random number, but at least roughly closer in terms of the concentration. So that if I now take this diluted NaOH here, titrate against HCl, 0.07 is a lot closer to 0.1, and who knows what that 0.1 actually is. Again, what I did is we did a titration. What we tried to do is we tried to pull 25 milliliter aliquots. Remember, I forgot to add indicator. Oh no, I wasted that 25 milliliters. For the very last try, I actually only took a 10 milliliter aliquot of it. So I just made a note of that. That was the HCl. Based on my titration here, I'm just going to give you the data again. The V1 from the base here was 16.22. The V final, so what did the burette say? This was the one that was really pushing it. It was getting really close to that bottom. I'm sort of lucky that it actually didn't overdo it there. But let's take the difference in volume. 49.23 minus 16.22. This gives you, in total, we had 33.01 milliliters. The second trial completely messed up because, whoops, I forgot to add indicator. Let's switch back to just using 10 milliliters now. For the V1 then, the V1 was 21.22. Notice I refilled it. I don't want to have to reload in between a trial. And then the bottom is 30.05. It was a little bit overshot, but what's neat here is I can actually calculate, well, which one here, what's the difference going to be if I did one with 25 mils and one with 10 mils. So 8.83. Usually you'd average these two, but this time they're totally different size aliquots, so we're just left with, well, we'll do the calculation twice. This time here, not as hard to see. NaOH here is going to react in a 1-to-1 ratio with our HCl. I'm going to just go straight to our calculations. We're interested in finding the unknown HCl. Let's do it from the data in trial 1. Trial 1, we knew the volume, we knew the concentration, both of them are the base. So let's take 0.03301, 33 milliliters. You just emphasize that there is base. The concentration after diluting is 0.0735 moles for a given liter. Our mole ratio is going to help us jump chemical. So for every 1 part NaOH is 1 part HCl. Remember to always balance the equation because it's not always 1-to-1. And then what we're going to do is we're going to divide it. Well, the HCl I decided to use the first time was actually a 25 milliliter aliquot. The word aliquot, A-L-I-Q-U-O-T. I'm going to divide it by that 25 milliliters. It also would have an error based on how precise your pipette was. But let's just crunch it through. 0.03301 times 0.0735 divided by 0.025 gives me 0.0970 molar. Looking at our sig figs here, because our titrant volume was something bigger than 4, it's good. I have 4 sig figs. But again, unfortunately, my grad cylinder didn't have that much precision for 8 milliliters. That was only 3 sig figs. I had to keep my answer just to 3. Just for comparison's sake here, let's see what we get for the 10 mil titration. So if I instead, this is good stoic practice for you, 0.0, let's say 883, 0.00 liters of NaOH. The concentration was still 0.0735, so I'm still down to 3 sig figs. My mole ratio is 1 part base kills 1 part acid. And then this one here was only in 10 milliliters, so let's divide it by 0.01000 moles over liters. We give you your concentration, 0.00883 times 0.0735 divided by 0.01. And this one here gives me here, well, very different, 0.0649. Especially when we're getting to concentrations that are so tiny, it's going to be, you need to be a lot more precise in terms of concentrations. So let me just double check my numbers here. But if that's what we got, that's what we got. 0.00883 times 0.0735 divided by 0.01. Yeah, so 0.0649. Right? So they were right. The HCl here is still approximately going to be 0.1 molar. But again, there's some variation because I somewhat overshot these ones here. I can't really believe in it. So what I would need to do is I would need to go back. Now I need to redo the dilution, redo the titration here to try to find the concentration. One thing that's not immediately obvious here, this is just practice of a titration technique. You'll notice that I've completely used up the diluted NaOH. What if the concentration was, the concentration is 0.0970, I know it, but I now don't have enough solution left over. That would be a waste anyways. So usually what you'd do is you'd actually make up a huge batch called a stock solution. You'd take a little bit of that batch, you'd actually use it, consume it to actually run into titration. Once you know the concentration though, you'd look back at your stock bottle and you say, that whole stock bottle is actually at this concentration. So hopefully that gives you a nice visual feel of some of the experimental problems that come in titration. If you have any problems, just let me know. Thanks, guys.